To find the equilibrium constant at a constant temperature, multiply the concentrations of the products and divide that by the product of the concentrations of the reactants. The coefficients in the equation become exponents for each compound's concentration. This is the equilibrium constant expression, but substituting in the concentrations, you get this expression. Using the concentrations, you get an equilibrium constant of 3.56 times 10 to the 8th.
The definition of Le Chatelier's principle is, if a change is imposed on a system at equilibrium, the position of the equilibrium will shift in a direction that tends to reduce that change. The ideal gas law can be used to predict many of these shifts.
Adding a product or reactant will cause the equilibrium to shift in the opposite direction in order to compensate. Removing a product or reactant causes the equilibrium to shift in that direction in order to reestablish the equilibrium concentration. For example, if I remove hydrogen gas, the equilibrium will shift to the left in order to compensate and create more hydrogen gas. Whereas if I add hydrogen gas, the equilibrium will shift to the right to use up the extra hydrogen gas and reestablish equilibrium.
An inert gas is a gas that does not participate in the reaction. The addition of an inert gas increases the total pressure but has no effect on the concentrations or partial pressures of the reactants or products, so the system remains at the original equilibrium position. For example, if nitrogen gas were added, it would increase the total pressure of the system but have no effect on the reaction or equilibrium concentrations.
When volume is reduced, the pressure inside the system increases. The system responds by shifting to the side with fewer moles of gas in order to regain the lower original pressure, and vice versa. The equation PV equals nRT shows the pressure and volume to be inversely related. When the volume decreases, the pressure increases. So for this example equation, the equilibrium will shift to the right because there are fewer moles of gas if the volume was decreased.
The value of K changes with temperature. Therefore, the amount of products and reactants present at equilibrium changes as the temperature changes. If a reaction is exothermic, like the one shown here, and energy is added by increasing the temperature, the reaction will shift to the left to consume the energy. This increases the concentration of the reactants and decreases the concentration of the products, therefore decreasing the value of K. The opposite is true for endothermic reactions, so the K value increases. To find the solubility constant, multiply the concentrations of the aqueous products.
To calculate the KSP using the solubility of a solid, start by writing out the KSP expression. To calculate the KSP from solubility, make an ice chart in concentrations instead of moles to find the equilibrium concentrations of the aqueous products. The solubility of Bi2S3 is 1.0 times 10 to the negative 15 moles per liter. So that is the concentration that dissolves. Using this ice chart, you can then calculate the concentrations of Bi3 plus and S2 minus after the solution is saturated at equilibrium. The concentration of the solid is irrelevant when calculating KSP. To find the value of KSP, you plug in the equilibrium value concentrations of the products and back into the KSP expression. Therefore, the KSP for this equation is 1.1 times 10 to the negative 73.
If given the KSP value, the opposite process is needed to solve for the solubility of a solid. Again, start by writing out the KSP expression.
The concentration of solid that dissolves will be represented by X. Using that, we can complete the ice chart for this reaction. Again, the concentration of the solid does not matter. Next, plug in the given KSP value and the concentrations of the products. Next, solve for X. This is the solubility of CuIO32.
A salt's KSP value gives information about its solubility, but comparing solids' KSP values is not always accurate in comparing their solubility. This depends on the number of ions that the salt dissociates into. Seen here, CuS dissociates into 2 ions, while Ag2S dissociates into 3. The KSP value of the salt with more ions is a lot smaller than the salt that dissociates into fewer ions. But when calculating solubility, the salt that dissociates into more ions has a greater solubility concentration. This is because more ions causes you to raise the concentrations to a higher power when calculating KSP.
If you dissolve a salt in a solution with a soluble compound containing one of the ions of the salt already dissolved, then it lowers the solubility of the salt, but not the KSP value if it remains at the same temperature. Before CaF2 dissolves, the major species are Na+, F-, and H2O. Therefore, there is already a 0.025 molar concentration of F- in the solution.
The concentration of the solid is irrelevant when calculating the KSP value. The initial concentration before the solid dissolves is 0 molar for the Ca+2, but 0.025 molar for the F- because there is already some dissolved fluorine in the solution. Then use X as the amount of solid that dissolves to find the relative final concentrations. Then plug in the final concentrations into the KSP expression. Because the KSP is so small, the 2x can be neglected to make solving for x easier. Because you are given the KSP value, you can then solve for x, which represents the amount of solid that dissolves, or the solubility constant.
The pH of a solution can greatly affect a salt's solubility. For example, with the dissolution of magnesium hydroxide, Adding OH ions increases the pH and therefore causes the reaction to shift left, thus decreasing the solubility of MgO2. Adding H plus ions oxidizes the OH ions to make water, thus removing them from the solution. This decreases the concentration of hydroxide ions and causes the reaction to shift right and the solubility of MgOH2 to increase because it must compensate and create more hydroxide ions. In general, if the anion X- is a strong base, the salt MX will show an increased solubility in an acidic solution. This is because the addition of hydrogen ions will oxidize the X- as a strong base and pull it out of the solution and decrease its concentration. This will cause the entire reaction to shift to the right and increase the solubility of the solid.